Thanks for having this. Thanks for letting me come and talk to you guys. Tonight I'm going to share some perspectives about how tech-rich, timeline-forward way that we embrace complexity could help shape the future in a positive way by using it to protect its own development. All right, let's go. The presentation's based on a paper that we're working on called Expanding the Scope of System Safety, Organizational Conditions, Control Adequacy, and Failure Escape in Consequential Design. The slides I'm sharing are going to help you see a few things that you won't like. I'm sorry in advance for some of the pictures you're going to see way up front. If you've got like a queasy stomach or something, I'm not going to show any blood, guts, or gore, but this is really about talking about designs that have consequence when they're not done right, right? So sometimes when we make mistakes, it can be harrowing. Most of the things that we're going to talk today about are essentially housekeeping that was important to do, but got overlooked. Because the abstracts they were using weren't granular enough to catch the variations that were important. So if I could tie in that whole piece about solid, I'm going to say that was a solid conversation. All right. I promised the bigger message. Oh my goodness, I've got to scroll. I don't like scrolling. There we go. The bigger message is that we can do better. And I'll try to hit the worst first and then head for the stars. Along the way, I'll drag you guys through some experiences that strangely ground the message. Let's go. It is going to go, isn't it? It's not going to go. How can that be? All right, never mind. I'm going to do this with the mouse. There it is. Just last week, Air Canada accident at LaGuardia, refinery burned, Port Arthur, Texas. What happened? Well, not what we wanted to. The airline crash. There was another emergency at LaGuardia. They were rallying emergency response to a particular accident. But they didn't shut the airport down, of course. So there was an error managing emergency response team directing a fire truck across a runway. The fire truck asked for permission. Air traffic control acknowledged the request and approved it. The fire truck lacked a position transponder. It's basically a GPS-based system that you can put on anything, like your Apple tracker or whatever. It's not high technology, but it's not required. Some places use it, like Denver. LaGuardia didn't. So what difference does that make? Well, the ATC has this map of the airport and the planes and where they're going and everything, and that would have told the air traffic controller that was a bad plan. The first thing he said after he gave permission was, "I made a mistake." 10 seconds after Air Canada's wheels touched the ground, the nose touched a fire truck. Right. I'm really sad that my controller isn't working. The refinery fire. The fire is likely due to a facility heater, right? One of these blowers that sits in the corner of the building and just maintains temperature. The processing equipment has all undergone hazard and operability analysis. Very detailed unpacking of what could possibly go wrong. Hanging right there in the corner. That's just the facility. Well, I'll tell you what. they maintain their equipment, they keep it on track because that heater wasn't considered part of the process. I'll bet it wasn't as well maintained. Guess what happens? When it breaks, it drops the liquid that's flammable, and the next thing you know, we've got an explosion. All right. I'm going to have you guys play a game with me. Are you all up for games? It's a really, really hard game. Who here doesn't know how to count from 1 to 100? Can you all count from 1 to 100? Yeah? Yeah. Okay. I have a 10 by 10 matrix. Your objective is to find the number 1, then find the number 2, then find the number 3, then find the number 4, while I time you. At some point you'll run out of time, and we'll talk about what's the highest number we got. Is that fair? Straightforward? All right, let's go. Go ahead. So you got plenty of time. Look at the green's going. You're just looking for 1, then 2, then 3, then 4. Keep track of your highest number. I might have given you too much time. Let's see if I can make it go faster. Come on. Come on, you can do it. There you go. Faster, faster. Keep looking. You want to get to the highest number, and then you're done. So, we had 100 numbers. Who got to 90, between 90 and 100? No?
Quick question, sorry.
Yeah.
Was it longest repeating step sequence the highest number? Like, was it just finding the highest 100 on the grid? I found 100.
You're supposed to count 1, 2, 3, 4, 5, 6.
Just in your head or?
You have to find each one. We'll do it again. We'll do it again. Oh, hey, that is better. Okay. Who got to 20? Who got to 10? Did you all understand that you did get to 10? 1, 2, 3, 7, 10. All right. 4. 4 is actually the most common answer, just so you know. The other guys are cheating, I think. All right, so this time we're going to do it again, but I'm going to help you, all right? Because obviously, you know, it was your first time out and stuff like that, but I'll help. Here we go. This time, I'm going to tell you that you can divide any matrix into 4, any square matrix into these 4 equal sides, right? And then if you look in the top left quadrant, they're prominently exposed as the number 1. You see that? And in the upper right quadrant is the number 2. You see that? And in this quadrant is the number 3. And in this quadrant is the number 4. And what do you think we'll find up here? The number 5. Okay? So with that little bit of extra structure, we're going to run the same thing again. So what are we doing? Just making sure we got it. We're counting 1, 2, 3, 4. All right. That's important. It's important that we all know our jobs, right? In safety critical work, if you don't know your job, you shouldn't be doing your job. And so we're just going to be that way, because that's how I am. All right, here we go. You already know how to get to 5, so it should be easy now, right? And it really needs to go a lot faster, because I don't have all that much time. Okay. Are you finding it? Because my little ADHD mind is like going crazy here. All right. Raise your hand if you got the highest number. You don't know, right? Who got less than they did the time before? All right. Who got to 15? Okay. Who got to 20? Who got to 30? All right. Very good. So what do we know? Even though if we could subtract off the first 5, that's still 25. That's almost twice as much as the last person lied about. Did the work change? No. We simply provided a structure for you to operate in under pressure, right? Did anybody notice that the pressure changes the way you behave? Yeah, because it was time dependent. Well, that happens in our workplace too. So in workplaces where we hire for high cognizance performance, if we then get up and get in their face, guess what? There's a cognitive depression. They go from 130 IQ down to 100 IQ. So you get to pay for all that high brain power and then just piss it away. There's other consequences. People under stress don't think through things. The whole point of high cognitives is the ability to check ourselves, to check those heuristic traits that we have that we slip into because it's a shortcut. All right. So round 1, we had capable people, a clear task, pressure applied. The score wasn't as good as we thought it should be. Round 2, the same people, same pressure, the environment changed, the score recovered. Quadrant mapping did not make you smarter, I promise. That score looked like performance. The higher number that we got represents the better amount of error checking that we have. Under pressure, we don't get as much error checking done. What if the thing you were searching for wasn't a number, but a latent design misunderstanding, or a misconception, or just a simple error? All right. So system safety is a profession in engineering. And our job is to review designs as they're coming about and seeing if there's gaps in what we expect the system to do and what we're going to deliver, because gaps can be a problem. There's a lot of different ways that gaps will happen, but I'm going to talk to you about some of the mental systems that are problematic. By itself, system safety works pretty well on a product. But the problem is that we don't just have products anymore. The design organization that generates the product is literally a product. We created a little black box that we turn the crank and out comes these hazardous products. All right, let's see what happens. So as we think about the way things are developed, we have to accept that people make mistakes. That's fair, isn't it? That high cognition workers are employed to minimize those mistakes, right? We're hiring the best. High cognition has a contextually limited bandwidth. We just saw that. Have you ever gotten a phone call when you're in the middle of a deep work session and it just threw you off? And then you had to figure out how to get back? On average, that's between 10 and 23 minutes to get back in flow. Usually that cognition drop is, I'm not going to say it's not noticed, but it's not recognized for what it is. You feel off. You regret not being where you were before the call came in. but you haven't quantified it. No one's saying, less smart than I used to be for a minute. Right? That doesn't happen. Well, that means risk increases. I'm not on top of it. I'm not on top of the work that I'm doing. I'm just trying to find my way back to my seat. But I'm still working because I don't want to waste that time, right? That was half of it. I'm sitting at my desk. I get an input. I can make a mistake. They expect me to do good. I only have a limited bandwidth. I misunderstand what I'm reading. That's bad, but that's my understanding. I looked at the picture. This is what I wound up with. Now, I take that understanding and I start working with it. I'm using the wrong information to start with. I don't know it, but that's what's going on. Then I make another mistake, and then risk is even increased more, and then I hand that to somebody else. But when I hand it to somebody else, they see this. They didn't see this. They didn't see this. They assume this is all that happened. Maybe that wasn't perfect to begin with. It's like Keystone Cops going on in my head. Has anyone, maybe you don't recognize the phrase, but I use the phrase garbage in, garbage out sometimes. That's that. And it happened between here and here. I'm just going to read this part. When systems can, in normal operation, lose the conditions required for maintaining safe operations, they're unsuitable for safety-critical applications. When we drop out, man, check your stuff. I'm not saying you all work in air traffic control, but there's an issue there, all right? In the real world, when safety-critical equipment isn't working, they take it out of service. The design organization doesn't even know that it's not working. They're saying, it's taking you guys too long to produce, go faster. Right? Under schedule pressure, cognitive overload, normalization, and it's not removed from the system, we don't even know what's happening. It continues producing safety-critical assessments and decisions without a flag, without a gate, without any understanding. Now the math isn't right. I'll be the first to recognize that the math isn't right. And not all these errors are safety-critical types errors. I overcooked my egg because I was looking at a spreadsheet. Unless the house burns down, I'm probably okay. But some of these could be safety critical. So the designers are making errors. And what you're not seeing here is that's one designer, and he passes it on under safety critical design under pressure to another designer who's getting the same end date but gets to start work later. And so between here and here, he's just thinking about all this time that he doesn't have, that the pressure's on and that we've got to perform it. He got his piece done, and now I have to perform it. It's like a relay race of errors. And then the reviewers, they get it way late. Has anybody ever seen a review organization get the data early when there's a time crunch? Yeah, no, that doesn't happen. So you get this multiplicative effect. And we're not tracking it. We don't know, and it could have been anything. Like, how many of you here have heard, this might be jargon, I don't know, the commute. You know what the commute is? No idea? Have you ever come to campus at 8 in the morning or tried to leave at 4? The commute, all right? Well, if you've ever worked in a design organization, before everybody gets there and they can actually start their meaningless meetings, they have this quiet time, right, that they use to review work product. I'm going to sit down at my desk in the morning and I'm going to review work product, get it off my desk, get it out of the way. But when I walk in my office and sit down at my desk or my cubicle or find a spot in the corner because there's no room for me, I'm thinking about the guy who cut me off in traffic. I'm trying to figure out whether or not I can remember if I packed a lunch for my kids. I'm trying to replan my carpool because Joe decided he was going to go to Europe and now we're all screwed up. I don't know. There's all this personal stuff comes in. And then we jump right into the most critical part, reviewing important work. I'm telling you, it multiplies. All right? There are tools. This is called SPAR-H, Standardized Plant Analysis Risk Human Reliability Analysis. Here are the critical characteristics. Under barely adequate time. That's not enough time. That's barely adequate time. And that's barely adequate for what are the normal blockers in the process. I have to go to a different floor to get my information into configuration management. I have to open a different application to whatever the stack up. If there's enough time to do the work but not any extra room, there's high complexity and stress, error rates increase 10 per function. Some of them might be safety. The cascade operates at every level. I have cognitive degeneration at the individual level. You saw that first string. And the second string, that's what I heard, that's how I process it, that's how I did my thinking about it, and then I spit something out and somebody else goes from there. Common mode failure. There has been a change in leadership. We are now changing our work schedule. The same thing that affects everybody takes down all of the error checking. It takes down all of our normal regulatory feedback. And what happens then? We start taking heuristic shortcuts without even knowing. Then the organization says, oh, we went through the review, that's good enough. We start at the beginning of the review, we ended at the end of the review, we're done. There's this normalization of deviance. The next time it's even easier. Well, we got it that way before. When you do it wrong and you approve it, you're basically giving provenance to something that doesn't deserve provenance. And you're setting a standard. Now, have you used checklists before? So if you use checklists to find things that rarely go wrong, you go through this process where every time you're saying the outcome is I check the box. The outcome is I check the box. Oops, I checked the box when I shouldn't have. The outcome is check the box. You just pave right over them. The output is failure escape. And in high consequence work, that's bad. Now, that seems pretty insurmountable. How do you get inside that? Well, I'm going to say that there's the possibility for a two-tier approach to handle this. Tier one, let's say I've got a designer who's working inside his application doing synthesis. He's actually building a design. He's got these little components of the design. Maybe he's working model-based systems engineering. Maybe he's working on an electrical circuit and he's got these elements that he's dropping in and he's creating a pattern. Now, if I have an AI aide, his sidekick, his buddy, and with singularity and singleness of purpose, at time X, his job is to track the pattern that's being built and map it to the engineering heuristics this guy was trained to, or that the application is about. So the minute that AI sees, oh, he's building AB amplifier, or he's using op amps to provide whatever, or he's using a code section for high-speed data transmission. The minute he starts seeing those bytes that represent something fundamental in training, the AI can now say, here are all of the trackable parameters that have ever made sense when we've used that design piece. So if I go to something as banal as a cantilevered beam, and Maria is building a new kind of diving board, so she's using a cantilevered beam. But I promise, the characteristics she's interested in are not the same as the architect who's building a porch roof over a 3-story building. The designers have something particular in mind and they're focused. But an AI, a learning machine, a quick pattern recognition cross-referencing tool could identify what all the parameters are, identify which ones the engineers think are important, and just catalog the rest in a database and say, we're going to track all of them, even though they're not all going to wind up in the spec. We're going to have them because complex systems have something called emergent properties. And we think that emergent properties are magic, but most often they're not. And most often they're not new discoveries of new physics. The emergent properties come because there's characteristics that come along with the design choices that we're not keeping track of. Now, Tier 2. This sounds really cool. Real-time cognitive performance monitoring. Boy, there's Big Brother for you, huh? The truth is, this stuff is already deployed. How many of you have smartwatches? Those features, a lot of them are in there. You can check your heart rate. Yep. You can tell positionally if you're moving around, if you've got jitters, if you're fidgeting. It's got little accelerometers in it. We cannot directly measure the disconnect when we come out of cognitive function, high cognitive function. But we can measure the symptoms. So what would that do? Well, let's say it just kept track of that and said, you know what? That bit of work he was working on there, it could be questionable. And we'll see how far it goes down before he actually circles back, because you know what? Maria is a competent engineer, and she knows that she should check her work many, many times. And if she had a choice and if time wasn't a burden, she'd probably jump on it right away and just stay on it. But we're in a rush. So if the work isn't reviewed, the AI could slightly elevate the scrutiny of the review. Just push it up. Would happen all the time. All right. What else? Now, if we require fault tolerance of the product, like the refinery itself, the equipment, it's supposed to be safe even if something goes wrong. It's not like a grenade where you can just pull the pin and say, well, it was safe before and something broke, so whatever. So if we require fault tolerance in the design of the product, Why not of the organization that's producing the product? 3 minutes? Oh, good, because watch. Oops. Darn it. There we go. So where's the work? Multiple fields are independently arriving at the same effort. They're focused in the same place. Each is working on their own way of thinking about the problem, their own accountability framework. System safety adds this overall holistic, we're interested in getting to a safe product going out the door, not I'm interested in making sure that this aspect is right or that aspect is right. So it's got an integrative, well, you know what I mean. The development gap is organizational recognition. It's not the technology. We are not challenged by the technology of doing this. So there's a white paper and probably some, I don't know, patent work or whatever. The symptoms have names like siloing. The outcomes are characteristics like interface failure. We know these things. The question is whether we're willing to examine the organizational control architecture that produces them. Questions? Sir?
Maybe I mentioned this earlier on, but with the introduction of training through those kind of pressure situations, see a cognitive increase as opposed to a degradation.
So, in general, training can help. And we see that with air traffic controllers. But ironically, in these high pressure, high importance stakes, typically those people have protected operating space. So they put them in the high pressure spot. It's high pressure when something's wrong. But they take them out and they recharge them. They put them back in and they treat their operating space almost sacred. That's not true in most production facilities. Anything else?
I just want to say I thought it was super interesting, you know, how like the viability of like an actors or whoever's, you know, cognition is assessed like in safety critical systems like that. You know, because I know it's definitely a thing, you know, coding wise, you know, context switching, right?
Right.
But the level of degree you can do that, you know, expand that. I was all trying to be mindful of that, but like.
So what I'm saying is that it's not happening right now, but it needs to.
Super, yeah, for sure, right? Super interesting when people think about that, I guess, for sure.
Yep.
That's trying to be accounted for in higher sensitivity systems, you know.
Yep.
And just also, yeah, is waterfall a big waterfall versus agile? I know you have like an idea of like reviewing early and often, you know.
Yeah, this is like keystroke by keystroke review.
It makes sense.